We'll record this one too. Any other questions? Okay, well, I'm gonna go through just some of the major concepts here then that you see. Let's look at number 2. One of the things you want to do with these different trig identities is be able to take exact values for some of these other trig functions. Now, some of the calculators, if you go on with the computer algebra system, they will do these exactly, and you can check all your answers. But again, I might say on there, show half angle identity or something like that to do it. So be able to do it without the calculator. This is actually important in theoretical situations to be able to do it without the calculator. But I don't want to ask questions that hard. So on 2A, it says, what is the exact value of the tangent of minus 75 degrees? All right. There's actually 2 ways to do this. Any angle that's a multiple of 15 degrees, recall, you can find the exact trig value of it either by the sum and difference formulas or by a half angle formula. So since 75 is a multiple of 15, you can use either one. Let's use the sum and difference formula and say, you know, I don't like those minuses. If I start having to do minus 45, minus 30, I'll get a lot of minuses. Maybe I'll make a mistake. You don't have to do this, but I like pulling the minus out from the start and say minus the tangent of plus 75 degrees. Now I can deal with a positive angle. I feel a little better. Right. And the one way to do this with the sum and difference identities for any multiple of 15 degrees is to write it as a sum or difference of 2 special angles. That's all it takes. And then apply a sum or difference formula, right? Tangent of alpha plus beta, if you like, or x plus y, is tangent plus tangent over 1 minus tangent. Right? So there is how you get this set up, and now it's just a matter of evaluating trig functions of special angles. We can do those either on the unit circle if they're big angles, or in this case, I picked small angles. I can put them in a right triangle. I don't even need to draw the unit circle if I can make these acute angles, right? So let's suppose this one is a 30, 60, 90 degree triangle. Then the sides are 1/2 square root 3 over 2 is 1. And I could say, well, what's the tangent of 45 degrees or 30 degrees? It's opposite over adjacent to 30 degrees. So tangent 30 degrees is 1/2 over square root 3 over 2. The 2's cancel since they're both denominators. I'll wind up with 1 over square root 3. Then I can look at the other special triangle, 45, 45, 90. Whose sides are square root 2 over 2, square root 2 over 2, and 1. And so the tangent is this side over this side. You don't even need to write this out. Since they're the same, obviously their quotient is 1. So I'll go ahead and put that in and say this is minus tangent of 45 degrees is 1, plus tangent of 30 degrees is 1 over square root 3, over 1 minus tangent is 1 minus 1 times 1 over square root 3. I didn't mention, I think this is a little harder exam than the other ones in general. Just the manipulation of the trig identities, it takes more practice. So do a lot of practice with these, and I think you'll do fine, but it does take more practice than the other two. Once we have to this part, one of the difficult things about this section is also the algebra. I can't give you full credit for that. I'll probably take 2 points off. What you want to do is get rid of these compound quotients, right? Quotients of quotients. So I'm going to multiply top and bottom by the least common multiple of the denominators I see, which is square root 3. I'll multiply the top by square root 3. I'll multiply the bottom by square root 3. And now I observe that this comes out to be square root 3 plus 1 over square root 3 minus 1. This is a point off still. I want to be able to get this radical out of the denominator. It turns out it'll be simpler. Sometimes it's not, but typically it is on these problems. If you have a plus b square root c, think this is 1 square root 3, then you can get rid of the radical by multiplying by a plus b square root c. So I'm going to multiply top and bottom by square root 3 plus 1. And I'll get rid of the square root 3 in the bottom this way, right? If I take this times this, FOILing, I get 3. This times this is plus square root 3. This times this is minus square root 3. They cancel. That's the purpose here. And then minus 1 times 1 is minus 1. So the bottom just becomes 3 minus 1, and the radicals are gone. The top, not so, they're not conjugates, right? Root 3 times root 3 is 3. Then I've got plus square root 3 on the outside, plus square root 3 on the inside is 2 square root 3. And then plus 1 times 1 is 1. So I've got this, and now on the top, combining like terms there, I got 4 plus 2 square root 3. On the bottom, I've just got 2. And there's a temptation to cancel your 2's or something. They don't cancel, right? You don't cancel from terms, you cancel factors. So I'm going to rewrite this by factoring 2 out of the top, right? This is twice 2 plus square root 3 on the top, and twice 1 on the bottom. Now 2 multiplies the whole numerator and the whole denominator. I can cancel it. And evidently this comes out to be 2 plus square root 3, except there's one more thing I forgot. I forgot to keep carrying my minus. I knew I'd make a minus sign error. This is why I'm suggesting go back and check your answers when you have a little time at the end. The really good students usually do that, and often they score better than I do. Right here to here, I dropped out my minus sign, so the whole thing has a minus. This is another reason to go through and check it in your calculator. Your calculator will do these exactly also. Some of these calculators will do exact expressions here. If you have one of those, or you want to do it online, you can use that symbol lab. You can try just Google that symbol lab, and it'll do that, these things exactly with steps in there. So I'll show you some steps about that. Is a good way to get some of these. You're welcome to use that for the test. Also, the Wolfram Alpha. This one won't show you the steps unless you give them money, but it will also do exact trig expressions. You just have to learn how to use it. So now I'm carrying my minus down here. Let me not forget it twice. Minus, and then I wind up with minus 2 minus square root 3. Better move the camera over.
Can you explain the 2 times 2 plus the square root of 3 step?
Yeah, I factored 2 out of the top. Like I said, 2 times 2 is 4. 2 times square root 3 is 2 square root 3. I pulled a 2, a factor of 2 out of each of these. So that's all I did. This times this gives the 4. This times this gives the 2 square root 3. And now the 2 multiplies the whole numerator. Now I cancel with 2 that multiplies the whole denominator, 1 that's left. That's the point. And then the minus out front distributes, right? Minus 2 and minus square root 3. So there's my answer then. The exact value of the tangent minus 75 degrees. Now you see why I don't like this one. This one's a whole lot easier, right?
Wait a minute. How does dividing the 4 plus 2 square root 3 by 2 equal negative 2 minus square root 3?
It's hard to see there. I've got a minus out in front of this whole thing. Minus the quotient, and then minus distributes, right? Think of this as minus 1 times 2 and minus 1 times square root 3. So I took minus 2 and minus square root 3. It's just hard to see the minus here, I suppose. I had to add it later. But that's why. Okay, so that's that one. You can also do this with a half angle formula. You could take tangent of 75 degrees is tangent of 1/2 150 degrees and use that one, but rather than do it that way, I'll do 2B where you're forced to use a half angle identity. While either of these methods, half angle identity or a sum or difference formula, will do any multiple of 15 degrees. Any angle that's not a multiple of 15 degrees, but half of an angle whose trig function you know, can be done by half angle formulas, and that's a larger group. For instance, suppose that you want to do these in radians. Suppose I wanted the cosine of 7 pi over 8, right? How can I do that? This is not a special angle. Furthermore, it's not a multiple of 15 degrees, pi over 12, right? This isn't multiple of pi over 12, it's multiple of pi over 8. But even though the sum and difference formulas won't work, the half angle formula will work because this is 1/2 of 7 pi over 4, right? Top times top over bottom times bottom makes it 7 pi over 8. Now that and 7 pi over 4 is a special angle, so if I write this as half of an angle whose trig function I know, I'll just go ahead and use the half angle formula. Now, if I think of this as cosine of 1/2 theta, the trig identity is the cosine is plus or minus square root 1 plus cosine theta all over 2. Gets the half angle out of there. And remember, there's 3 half angle identities. You should have these memorized. It will help you on the test and it will help you in future classes. If you take cosine of 1/2 theta, it's plus or minus square root 1 plus cosine theta all over 2. That's what I used here. And they're not too hard to memorize, even though this is kind of complicated. Once you have that one, you can get this one, right? Sine 1/2 theta is the same thing.
Oh,
Just change plus to minus right here. 1 minus
Right.
cosine.
you might want to shift it over to the side.
Say again?
You might want to shift the camera over.
Yeah. Yeah, thank you. I have it over. Yeah. All right. And then the last one, so the cosine, you memorize this formula. Sine, all you do is change plus to minus, you've got the sine memorized. Take the quotient of those two and you've got tangent, right? Tangent is sine over cosine.
Oh, and you might want to shift it up a bit because I can't see the top equation.
Okay.
What? Yeah. Oh,
Okay.
there. And now the layout button is blocking my view of the part of one of them. Thank you.
Uh-huh. So if I take this one over this one, the square root 2's will cancel, and I'll just be replaced with this over this, 1 minus cosine theta over 1 plus cosine theta. So it's not hard to know all three. If you just memorize this one, change plus to minus to get the sine of 1/2 theta, take the sine divided by the cosine to get the tangent, canceling the square root 2. All right, so I'll use the first one in here. But it's easy to memorize these half angle identities, and they do come up quite commonly in higher mathematics. Now, 7 pi over 4, I do know. However, I can't do it in a triangle. It's not an acute angle, right? So I have to say, what's 7 pi over 4? 8 pi over 4 would be 2 pi, right? So it's almost 2 pi. It's 8 pi over 4 less pi over 4, right? So this will be my 7 pi over 4. There's a whole rotation back up pi over 4. That means this angle that's left is pi over 4, so they add up to 2 pi. Now I can drop a perpendicular. Figure this triangle, right? There's the reference triangle. Since it's a 45-degree angle, this is square root 2 over 2. This one's square root 2 over 2, and this one's 1. And I can say, well, cosine then is the x-coordinate is square root 2 over 2. So let's see. And then is it plus or minus? You're tempted to say 7 pi over 4 is in the fourth quadrant, cosine's positive. But what I'm really wanting to sign here is that I'm evaluating cosine of 7 pi over 8. That's a little less than pi, right? Pi would be a half rotation. This is a little less. It's over here like this, right? It's 7/8 of that angle. And so it's in quadrant 2. Okay. So this is in quadrant 2. In quadrant 2, cosine negative, so I want to take the minus sign, whatever this angle is, not what this angle is, to pick the plus or minus in front. So I've got minus the square root of, and now cosine I figured of 7 pi over 4 is in the 4th quadrant. There it's positive. So this is 1 plus square root 2 over 2 all over 2. And now I need to simplify that. Again, it's 2 points off at this point because there's compound quotients and there's more. How do I get rid of that? I multiply the top and bottom by the denominator here, 2. I'll multiply the top by 2. And I'll multiply the bottom times 2. And now, 2 times 1 is 2. 2 times square root 2 over 2 is square root 2. All over, oops, sorry, 2 times 4. 2 times 2. Multiply top and bottom by 2. And the bottom I have 4. Once again, I got a square root of a square. I want to simplify that. I'll write this as minus square root of 2 plus square root 2 all over square root of 4 is 2. There's a good answer like that. Technically, in algebra, you can often simplify these things. Square roots with square roots inside. However, it's not simple, and we'll just leave it here. I think this is the answer I put in the back for the practice problems. Everybody feel good about that? 2 different ways to do non-special angles. Any multiple of 15 degrees, you can do either a half angle formula or a sum or difference formula. If it's not a multiple of 15 degrees, but half of some other angle whose trig functions you know, you can use a half angle formula. Like this one is half of 315 degrees. All right, does that bring up any other particular problems you want to see?
How did you get the 2 instead of the 4?
Oh, I rewrote this as, I don't think we did anymore. Minus, square root of the top over square root of the bottom. I just left out one step there. I have a square root of a quotient. That's equal to the quotient of square root for positive numbers. So I wrote it like this, and the square root of 4 was 2. Is that okay? Did I answer the right question?
That helps, thank you.
Okay, good. All right. The double angle identities, I also want you to know. I better move that camera, I suppose, huh? Is it all right? Yes, it's all right. Here's number 4 off the set. Use a double angle identity to find the sine of 2x. Exactly. If secant of x is square root of 5 over 2. How about that? This is kind of a classic problem in trigonometry books. There's a good chance you'll get it. It was on the homework and it's on the practice test too. Here's what you can do. If you're asked to find a trig function of a double angle, immediately write down the double angle formula. Sine of 2x is not this. Somebody's going to do this on the test. Pull the 2 out. You can't pull the 2 out, right? I tell people if you've got square root of 4x, you don't just pull the 4 out and say, oh, it's 4 square root x, right? You say by the product rule for these, it's square root 4 times square root x. And so it's 2 square root x, right? You can't just pull the 4 out of the function. Neither can you pull 2 out of the sine function. Sometimes to save writing, we'll write this, but it means there's still parentheses there implied. It's just for brevity that we leave the parentheses out. So this isn't true. Instead, what you do is you memorize the double angle identity. Sine of 2x is 2 sine x cosine x. There it is. So it looks like that. Write down the double angle identity. And now say, what do I need to be able to do this? I need sine and cosine. I'm given secant. But I remember that given any one trig function, I can find all 6 trig functions, trig function in a quadrant. And I guess I left part of this off, didn't I? And sine x is less than 0. So I need to know a quadrant also, or it'll have a plus or minus sign that's undetermined. But given a trig function in a quadrant, I can do it. Well, tricky, I didn't give you the quadrant. What am I going to do? If secant x is positive, that means its reciprocal cosine x is also positive. Right, it's 2 over square root 5. And if cosine is positive and sine is negative, then I can think in my head, positive x and negative y is over here. I'm in quadrant 4. So for this, I can figure out the quadrant from the sign of secant and the sine function. In quadrant 4, then, I'll go ahead and compute this. All right, so sine of 2x is 2 sine x cosine x. Now I need to get both of those. Once I know what I need, so I have a trig function in a quadrant, I can find all 6 trig functions is the point. All right, so cosine x, I can get from secant, it's just the reciprocal of secant. Right? So it's 2 over square root 5, just turn that close outside. Now, once I have cosine, I always know I can get sine because of the Pythagorean identity solved for sine, right? Sine squared plus cosine squared equals 1 is our Pythagorean identity, the very important one. One of the more important ones in trigonometry. I can solve that for sine by subtracting cosine squared and taking the square root, right? This says sine. If the square of sine is this number, the sine can be plus or minus its square root, right? There's always 2 answers for any positive number here. So sine x is plus or minus square root 1 minus cosine squared. I can use that, the Pythagorean identity solve for sine whenever I get cosine to get sine. A lot of engineers, it seems like, do this. Sine x is plus or minus the square root 1 minus cosine squared x. Is it plus or minus? This is where I need the quadrant. We said cosine is positive, sine is negative. We must be in quadrant 4. In quadrant 4, or just look at this, sine is negative. Right? So this is minus the square root 1 minus 2 over square root 5 squared. Is minus the square root of 1 minus 4/5 is minus the square root of 1/5, which you might then prefer to write as minus 1 over square root of 5. Again, writing this as minus square root 1 over square root of 5, square root of the quotient of the square roots for these positive numbers. And then minus 1 over square root of 5 is simpler than this, right? Now, that's what you do. You write down the double angle formula to figure out which trig functions of x you need. You can calculate them both because you're given another trig function. Then just plug these in. And so sine 2x is twice. Sine x I calculated as minus 1 over square root of 5 here. Cosine x is 2 over square root of 5 from here. When I multiply these out, right, just treat 2 as 2 over 1, take top times top times top is minus 4. Over bottom times bottom times bottom is 5. The exact answer is minus 4/5. I don't know what the angle is even, but I can figure this exactly. You can't just do this in your calculator, right, or on symbol lab or something like that. That's part of the reason they put the problem this way, is to make you use the identities. You probably get something like that either for a half angle or a double angle problem, like both. Another topic is solving trig equations. So you want to be able to use identities to do these kinds of things. Suppose I said solve this trig equation. Find all solutions exactly. By the way, when I'm between problems, ask me if there's any other problems you want to do some you ask for. Find solutions exactly to this problem. Secant 2 theta. This is 6p, by the way. Equals minus square root 2. What are all the exact solutions to that? If I don't say between 0 and 2 pi or something like that, then there's an infinite number of solutions in general. And I just said all angles theta. So how do I do this one? I have trig function equal to number. First thing you do is if it's not just theta, but a multiple of theta, is you make a substitution. Let phi, or whatever your favorite letter is, be 2 theta. You put x here. And rewrite it as secant phi equals minus 2, square root 2. Find all solutions phi and then substitute back to get theta. How do I solve secant of an angle equals a number? Remember, for secant and cosecant, you just write the reciprocal. So I'll rewrite this reciprocal of the secant as cosine equals the reciprocal of this one is minus 1 over square root 2. Now I can solve this on the unit circle, right? Because after all, cosine is the x-coordinate of the unit circle.
Very much from you.
Am I off yet? Go ahead.
Never mind. The video just came back up on my end.
Oh, okay. So here's the unit circle. And I want the x-coordinate to be minus 1 over square root 2. X equals the number is a vertical line. Here's all the points. X equals minus 1 over square root 2, around minus 0.7. I observe there's exactly 2 points on the unit circle where the x-coordinate is minus 1 over square root 2. Consequently, exactly 2 terminal rays are possible within 2 terminal rays are possible. And that makes 2 angles within 1 rotation. This one, and that's it. All right. So what is this angle here? Well, it goes out to x equals minus 1 over square root 2. That means that this length here is plus 1 over square root 2. That's the length, so I'll call it positive. You can write negative on here, it doesn't hurt anything. A lot of people do that. I just like to put positive lengths on the triangle side and then put the coordinate negative. All right, so there's 1 over square root 2. You might also recognize by multiplying top and bottom by square root 2 that that's square root 2 over 2, the side of a 45, 45, 90 triangle, right? So that gives you the hint. That's what this is. It's square root 2 over 2 here. It's a unit circle. That's 1. That forces the last side to be square root 2 over 2 in a 45, 45, 90 triangle. So here's the angle here, pi over 4 radians. Right? And by symmetry, the other angle is always the same. This will be pi over 4 also. Now I have it, right? In order for cosine to be minus 1 over square root 2, I have these 2 angles within 1 rotation. Pi back up pi over 4. One rotation. Pi minus pi over 4. Remember how to do these, right? Write them over a common denominator, right? 4 pi over 4 minus pi over 4. Then you subtract the numerators, 4 pi minus pi over the common denominator. Gives you 4 pi minus pi is 3 pi all over 4. That's what this angle is. It's 3 pi over 4. Then I have pi plus pi over 4 is the other one. Do the same thing, right? This is 4 pi over 4 plus pi over 4 makes 5 pi over 4. And the numerators over the denominator. Those are all angles within one rotation, but I said find all solutions. I didn't write it out all the words here. So now what are all solutions? These are the only two terminal rays, so all the rest of the solutions are just these plus whole rotations, right? So all solutions, which is what I asked for, are these angles plus 2k pi, right? K rotations, including negative possibilities. So theta equals 3 pi over 4 plus 2k pi, or 5 pi over 4 plus 2k pi. There's the answer you want. Don't give me a decimal on there, it's no credit, unless you show me some of this work. All right, there's finding exact solutions.
So would we not add 3 pi over 4 as an answer without the 2k pi?
You can, but I said I want all solutions, so that would just be part of the answer. And if you wanted, you could write some of them out. You could say 3 pi over 4, and then what's 2 pi added to that? Be 12 pi over 4 added, let's see. 2 pi would be 8 pi over 4 added to that, so I could write 11 pi over 4 by adding 8 pi to this, and then I could write 19 pi over 4. Then I also have to go the other way. So, these two answers are only part of the solution. I want to say this to get all solutions. If I say find all answers between 0 and 2 pi, then yeah, these are the answers. But if I say find all angles, you have to put the 2k pi in both. You can write this instead. I'll accept that instead of these, but I think this is harder. This will be the first one, and then the other one would be 5 pi over 4, and I'm going to add 8 pi over 4 would be 13 pi over 4, and I'm going to add 8 pi over 4 and get 21 pi over 4. Then you have to go in the negative direction too. So there's an alternate answer, but I don't recommend it.
On the answer sheet, it says theta equals 3 pi over 8.
Did I mess it up? Oh, yeah. You know why? Yeah, you're right. Thank you for pointing that out. I messed it all up. Because I forgot this was solving for phi, right? I solved phi. This is why I tell you guys check your answers, because what happens is some of you do better in the test than I do, because I just do a 1-through usually. And then as I'm grading, I'll find out, wait a minute, they're right. You have to go back and check these. Yeah, phi was equal to 2 theta, and so this was phi equal to these, right? All solutions phi. Thank you for pointing that out. And then you have to, phi is equal to 2 theta, and so you divide this through by 2. And so you get theta is 1, you have to divide both these by 2. It's 3 pi over 8 plus this divided by 2 is k pi. And this 1 over 2 is 5 pi over 8 plus this one divided by 2 is k pi. Thank you so much. All right, let's try another one. Another thing you want to be able to do is like number 6. I'm sorry, number 7. Let's do 7b. This is probably the hardest one on the practice test here. It involves the most calculations. And if you can do this one, I tell people, I think you've got a pretty good handle on this whole chapter. So good chance you'll get something like this on the test, because I can test you on everything. Just about, not everything, but a lot of it. This one says, solve for theta between 0 and 2 pi. What does that mean? One rotation, and I want your answer in radians, right? If I put this, I mean, put the answer in radians. On the last problem, if I don't say degrees or radians, you can do either and I'll accept it. But if I write this, I want radians, and if I write this, then I want degrees, right? It's not a big take off, but if you don't put it in the right units, I might take 1 point off. All right, so 7B. Suppose I have this one,
Can
2.
you turn the camera really quick?
Oh, sure, I thought it was on. I see the edge of the screen on my end. I thought, oh, maybe I don't. Thought I saw that. This thing's small. Sometimes I think I see something that's not there. Sorry about that. 2 secant squared theta minus 2 secant theta minus 3 equals 0. On this one, I gave you a hint, use the quadratic formula, because I didn't want you to fluster and flail trying to do it a harder way. How do you solve something like this that has one trig function of theta, but there's a square in here, right? The hint is to let x equal a trig function and see what the equation looks like algebraically. Now what I get is 2x squared minus 2x minus 3 equals 0. Maybe I recognize it's a quadratic equation in x, right? All this was a quadratic equation in secant theta. Now that I see this form, I can apply the quadratic formula, or I can factor, depending. When you can see how to factor immediately, like if it says x squared minus x equals 0, factor, right? It's easy. This factors is x times x minus 1 equals 0. So factor when it's easy, it's faster. But this one, the numbers look kind of funky here. I think maybe I'll try the quadratic formula, because sometimes it's extremely difficult to factor. So hard that you have to know the quadratic formula in some cases. In this case, I give you a hint using the quadratic formula. You probably ought to try it. So here's what I have. It's ax squared plus bx plus c. Make sure this whole thing is on the left, so you have 0 on the right. If you don't, if you put the 3 over here, then you might use c equals 3 in the quadratic formula instead of c equals minus 3. Put them all over on the left and 0 on the right before you use the quadratic formula. So you get the right sign, plus or minus on each of these. So x now equals minus b is plus 2, plus or minus square root b squared is minus 2 squared, minus 4 times a times c, like that, all over 2a. And let's see what we get. This is 2 plus or minus. So this always works. It always works. If you get square root of a negative, that just means there's no solution. Okay, 4 plus 24 is 28. All over 4. Good thing I didn't try to factor. Do you see how this would factor if I tried to factor this? Here's how it factors. You factor out the coefficient of x squared. This is just for your education. Don't do this for the test. Twice x minus blank, x minus blank. It does factor this way, and guess what goes in the blank? So what you do is you take the lead coefficient times x minus blank, x minus blank. You can always factor it that way. Sometimes it has the square roots and negatives in here. That's the hardest case, imaginary numbers. But you won't get that here. But what goes in these blanks are precisely the solutions to quadratic formula. I'm going to reduce this because this is not as simple as can be. Square root of 28, right on the side, is square root of 4 times 7 is 2 square root 7. I can rewrite square root of 28 that way. And I'll write following now. I notice I can factor out a 2 from the numerator. You can't cancel this part of this 2 with a 4, right? You don't cancel things in terms. You have to cancel factors. So factor 2 out of the top, right? The top is 2 times 1 plus or minus square root of 7. And the bottom is 2 times 2. Now 2 multiplies the whole top, 2 multiplies the whole bottom. They're factors, we call them when they multiply the whole expression. So we can cancel those factors, and the solutions are 1 plus or minus square root 7 over 2. And if I would have tried to factor, this is what goes in the blank. 1 plus square root 7 over 2, 1 minus square root 7 over 2. How would I ever guess to put those things in the blank, right? So factoring was a bad idea in this one. You can use the quadratic formula and get it straight out, though. So I'm gonna scratch this out saying this is just for your education. That if you take higher courses, this is useful to know this. All right, now that I know X is those solutions, now I can put it back and say X is 1 plus square root 7 over 2 is one solution, or X equals 1 minus square root 7 over 2 is another. But X was secant, so I'm actually solving secant equals this number, or secant equals this number. Now I've got it. The purpose on these advanced trig equations is to rewrite it as trig function equals a number and go back to the unit circle. So that's what we did. We got trig function equal a number. Two different cases now. We go try the unit circle. How do we solve secant equal a number? Remember? Rewrite it as cosine, right? Take, if these two are equal, their reciprocals are equal. Cosine theta is 2 over 1 plus square root 7. Right, and this one is cosine equals 2 over 1 minus square root 7. All right, so now, how do I solve cosine equal a number? I draw it with the unit circle. And I draw the vertical line, right? Cosine is the x coordinate. X equals this number, all right? Well, this is a positive number, right? Because it's positive over positive. So it's going to be over here somewhere. And I don't know exactly what that number is, but I'll just draw it anywhere. I just don't want to put it on this side. So here's maybe x equals 2 over 1 plus square root 7. Since this is less than 1, I observe, right, it's 2 over something bigger than 2. I observe it's going to intersect here in 2 places. And so there's going to be exactly 2 terminal rays wherever they are. 2 solutions to this one within 1 rotation. Now the other one, however, if I go to sketch this one in the unit circle, square root 7 is between 2 and 3, right? Square root of 4 is 2. Square root of 9 is 3. So this is between 2 and 3. 7 is between 2 squared and 3 squared. Now, if I take that, subtract this, I'll get a number that's between -1 and -2, right? If I take 1 minus 3, I get -2. 1 minus 2 is -1. And I notice that the denominator is going to be between -1 and -2. So this quotient is actually going to be less than -1, right? 2 over a negative number that's small, that's not as big an absolute value. In other words, vertical line is out here. This number is less than -1. You can run it on the calculator. I like to do this without the calculator, but just run this on the calculator. See, this is less than -1. And so I plotted over here outside the unit circle. Observe that there's no solution. So I'll say no solutions to this case. But there are solutions to this case because this is 2 over a bigger number. This is a line between 0 and 1 here. So I have only now the solutions. Cosine theta equals this number. So what are these 2 angles? This is what makes this the hardest problem of a practice test. What are all the solutions to cosine equal this crazy number? It's not a special angle anymore. I want you to be able to do non-special angles. Well, one solution is always the inverse cosine, right? Provided it has a solution. This one doesn't. This one, theta, will be the inverse cosine. 2 over 1 plus square root of 7. Right? How do I know it's not this one, or this one, or this one? Remember, the inverse cosine is always an angle between 0 and pi, or 0 and 180. So it's in first or second quadrants, and not this one. And it's not all the way around 2 times in here or back this way. It's right, this one right here. So that's the arc cosine. Knowing that, now I know by symmetry, this must also be the arc cosine, right? This is the same angle as this one, just by symmetry. Arc cosine 2 over 1 plus square root of 7. That means my 2 angles between 0 and 2 pi are this one and this one. So I observe, and these doesn't contribute any new solutions. So I observe there's only 2 solutions. They come from this one. One of them is theta equals arc cosine 2 over 1 plus square root of 7. And the other one is, well, let's see, 2 pi back up that same number. 2 pi minus arc cosine 2 over 1 plus square root of 7. So once you do this one in the calculator to get an estimate, you can just subtract from 2 pi to get the second one. It's kind of easy like that. If I asked you for exact answers, these are the exact answers. I'll box this even though it's not the final answer. Because it is real useful in higher classes in chemistry and physics and engineering. Often you want the exact answer, you write it in this form. However, the solutions say solve for this in 0 to 2 pi, round to 2 decimal places. That's going to give you a hint right off that it's not a special angle. If it's a special angle, I'm going to ask for the exact answers. Even though it's useful in lots of theoretical calculations to have the exact answers, if you're actually out in the field, it's also useful to be able to say how many degrees or radians is that, so you can measure it out on your device, right? So let's also follow the instructions around the 2 decimal places. And if I take the inverse cosine, I have to make sure this time my calculus in radians, partly because I asked for answers in radians, and partly because this is a measure in radians. If I do this one in degrees, mix radians and degrees, I'll get the wrong answer right for either case. So let's try this clear. Make sure it's in radians, and it is. We'll take the inverse cosine, you push second cosine, and you want to be able to do this in your calculator for the test. If you don't have a good calculator, you can use Symbolab or lots of other online calculators to do these things to decimals. So there's lots and lots of them. I'll say, okay, so arc cosine 2 divided by this whole quantity, 1 plus square root. Seven. And I get 0.99 and other stuff. Rounding to 2 decimal places is just this one. Then I'll take 2 pi minus that one. So I'll take 2 times pi minus the answer that's on the screen. And now I get for this one 5.23, etc. And round to 2 decimal places means count 2 digits right at the decimal point. And if the next digit is 5 or greater, round this one up to the next digit. If it's not, then leave it as it is. So we'll say this is approximated by 0.99 for the first one and 5.29 for the second. It's a comma. Hopefully that's what it says on the back. I have to check these. This one is so complicated. I make mistakes when I do it. Yeah, we got it right. Okay, good. questions on that one? That's the hardest one. Actually fit it on the board, I'm pleased. Okay, so the other trig equations, if it's not just trig function equals a number, you use some algebra to reduce it to trig function equals a number and then solve it on the unit circle. Oh, I know what else I was gonna say too. A lot of people will have trouble getting the right answers on the calculator once you get here. To do this arc cosine, here are the buttons you push. You push second cosine, or sometimes it's FCN for function or something like that. Because up above, the second button will enable the arc cosine above. Make sure you're in radians mode since we want the answer in radians. So put in radians mode first, then push second arc cosine. And we'll automatically insert a parenthesis. Now we need 2 divided by, and there's a trick here, right? Since if I don't put parentheses around the bottom part of the calculator, it will assume that it should divide to the division before it does the addition here. So I'm gonna put that in. A lot of calculators have a long divide key these days, and so you may not need to do this, but you may need to put parentheses here. 1 plus square root is second x squared on the TI-84. The square root's up here, so you get it like that. Well, some calculators, again, they're different, so you might be a little different than this. The divide, if it has a long divide, then you maybe just arrow down at the bottom rather than put a parenthesis. So there's square root of, and then I need 7. Then I need to close the parentheses for this that are automatically inserted for the square root. So I might need to put a closed parenthesis here for the square root. I do in my calculator, it's an old one here. And then I need to close this parenthesis that I inserted. And then calculator may or may not put 2 parentheses for the cosine. So that depending on the calculator, I may need to close this one. The TI-84 automatically closes all the parentheses. So you just check it real easy. But it ought to look like this. It ought to say arc cosine parenthesis 2 divided by parenthesis 1 plus square root 7. I can mess it like this. Close parenthesis. Close parenthesis. So this ought to appear on the screen. Then you know you got it right. So the point is make sure it divides the whole thing here. You have to push enter to evaluate it. And then to do the second one, you push 2 pi, so 2 second caret usually has the pi above it. So second caret will give you pi to lots of digits. If you want, you can memorize them 3.14159 to enough digits. That's fine too. So second pi puts pi on the screen. 2, oops, I need 2 times pi, don't I? Sorry. 2 times second pi. And then minus, and you can get the last answer you had by pushing second and this little minus key down at the bottom on the TI-84. Sometimes it's a different key on other calculators. It says A and S up above. Then you push enter. This one calculates 2 pi. This one puts A and S on there, subtracts the answer from the last one, which was the arc cosine, and then the enter evaluates it. That's a nice way to do less keystrokes than to retype the inverse cosine all over again. All right, let's charge ahead then. Here's another one. If I look at 8c, solve these exactly for theta between 0 and 2 pi. Tangent 2x plus 1 equals 0. off the screen here. Tangent 2x plus 1 equals 0. So this is a tricky problem, right? That's why I say these take practice more than the other chapters. Not rote memorization. This one, we said there's a list of rules. Well, let's say this is what we call a linear equation in a trig function. A number times a trig function plus a number equals 0. We can solve this by converting it to trig function equals a number and then applying the unit circle. So we'll do that. However, we also have this angle 2x. So I recommend doing this. Make a substitution. Call this theta or something, and solve tangent theta plus 1 equals 0 on the unit circle, and then we'll go convert back when we're done. So with this one, I'm also supposed to have theta between 0 and 2 pi, which tells you coincidentally I expect your answer in radians to be a point off, right? All right. Tangent theta plus 1 equals 0. I just subtract 1 and rewrite it as trig function equals a number. Now, once it's trig function equals a number, I solve it on the unit circle. Tangent, alas, is the hard one, right? I'm going to rewrite this as tangent x equals minus 1, tangent theta equals minus 1. But tangent theta is y over x in the unit circle, not to be confused with this x in the original problem. I just put x here for the unit circle. And how can I make the quotient on the unit circle equal to -1? Well, I rewrite this as minus square root 2 over 2 over square root 2 over 2. That's another way of writing -1. Right? But this point is on the unit circle, just for memorization. How do I know to do this? I can do some more steps, although I think it's easiest just to guess this after a while. Rewrite this as a quotient, minus 1 over 1. Right? And then divide top and bottom by the root sum square of these two numbers. Square root of minus 1 squared plus 1 squared is square root 2. So now if I divide the top and bottom on the quotient by square root 2, now I'll recognize this will always be a point on the unit circle. So I can take this to be y and this to be x will be on the unit circle. That's what I need, is a ratio on the unit circle whose tangent is -1. Now there's a second ratio too, don't forget. You can take minus the top over minus the bottom and rewrite this as plus 1 over square root 2 over minus 1 over square root 2. That's also a point on the unit circle. There's always two answers. One with the first quotient you come up with, one with minus the top over minus the bottom. All right, so you can, the easiest way is once you see -1, just to guess, to rewrite that as minus 1 over square root 2 over plus 1 over square root 2, or plus over minus. But if you forget, you can root some square of these and figure out what to put in there. Evidently, this is a pretty hard problem too, isn't it? I can put this one for y and this one for x, so y would be minus 1 over square root 2. It's about -0.7. And x will be plus 1 over square root 2, about plus 0.7. And here's the point on the unit circle. There's my terminal ray, where this is y and this is x for the tangent. Now, the other angle here is always directly opposite. This is what makes the tangent cotangent cases the hardest. Right? But if you plot it, now y is positive and x is negative. So we go to square root 2 over 2 minus square root 2 over 2, and sure enough, it's directly opposite. So what's the solution set here? I can find all angles theta. What are they? Well, drop the perpendicular, and you observe And since you went down to minus square root 2/2 here, there's a minus here. This side length is square root 2/2. Since you went over to plus square root 2/2 here, this is plus square root 2/2. That's a 45, 45, 90 triangle. This must be an angle pi over 4, right? And by the same token, this one's opposite is always the same measure, that's by symmetry, is pi over 4. So all angles theta that satisfy this tangent theta equals -1 are this one or this one, plus any whole multiples of 2 pi, so that you can get the same terminal right. So the all angles theta are theta equals minus pi over 4, going clockwise for this one, plus any multiple of 2 pi, or the opposite angle. This one would be pi back up pi over 4. It's 3 pi over 4 plus 2k pi. Now, you know what's better than writing this? This is right, and I'll count it right on the test, and we aren't done actually. But what's easier when you have symmetrically displaced angles, whether there's 2 of them or 4 of them or something like that, is just put one angle plus the turn to the next angle. If I take, say, this angle, 3 pi over 4 plus pi, plus pi, plus pi, and I can go -2, then I'll get all angles in an easier expression. So equivalently, with an easier expression is to say theta equals either one of these angles. Let's say, just to make this interesting, minus pi over 4, the first one, plus k pi, k half rotations gets me this one, plus half rotation, plus half rotation, half. Gets all the angles too. So this is the same as this, but shorter to right. Alas, I'm not done still, right? Because theta was what I put in for 2x, right? Theta equals 2x. So now I've got 2x, not x, and then k is any integer, any number with nothing after the decimal point. So I divide that through by 2. I have to divide this by 2, divide both of these by 2, and I've got x equals minus pi over 8, dividing that one by 2, plus k pi over 2, dividing the other one by 2. How about that? Pretty difficult. But this is all solutions x. Now, the last thing is I said, oh, wait a minute. Oops, I wrote theta between 2 places. I said x. Now I finally have to find x within one rotation. So this is all solutions x. Keep only x between 0 and 2 pi as required. I think it's easier just to find all of them and then throw out the others. Otherwise, you have to find theta between 0 and 4 pi, so that x will be between 0 and 2 pi, and it's complicated. So I'll let x, I'll keep only those between 0 and 2 pi. So I try small numbers like k equals 0, and let's see, minus pi over 8 plus nothing makes a negative angle. That's not between 0. I need to make it bigger. So I'll put k equals 1. I get minus pi over 8 plus 1 pi over 2. Well, I need to put a common denominator. This is minus pi over 8. Multiply this on top and bottom by 4, and I get 4 pi over 8. It's 3 pi over 8. That's between 0 and 2 pi. So this is one angle. Then I can put k, so that's k equals 1. I put k equals 2. And I get minus pi over 8 plus 2 pi over 2 is pi. Well, that's minus pi over 8 plus 8 pi over 8 is 7 pi over 8. And you start to see a pattern here. They're just increasing by 4 pi over 8 each time. If you don't see it, just calculate the other. But if you put k equals 3, what you'll get is minus pi over 8 plus 3 pi over 2. Just putting k equals 3. Comes out to be 11 pi over 8. This is also between 0 and 2 pi, right? 2 pi would be 16 pi over 8, right? So, and then I've got one more, k equals 4. I'll get minus pi over 8 plus 4 pi over 2 is 2 pi. Oops, wait a minute. Yeah. And so 2 pi minus pi over 8 is less than 2 pi, so it's still good. All right, this is going to be 15 pi over 8. 4 answers. The next one is going to be bigger than 2 pi, so I can stop right there. So a pretty tricky problem, I think. Questions on that one? Well, last but not least, we have some problems on verifying identities and simplifying trig expressions. So we want to make sure we look at one of those. When you do those, remember those 3 rules. You apply algebra to get rid of compound quotients, cancel common factors, etc. All the things you do in algebra. You can apply a trig identity, and then if you're stuck, rewrite everything in terms of sine and cosine. Then repeat. Go back, algebra, trig identity, write in terms of sine and cosine. And just do that over and over. With one rule at the beginning, you first run it down to just one angle. So you don't have sine of 2 theta here and sine of 1 theta over there. So let's do this one. Let's try 12A. Well, I said simplify this. And by the way, verifying trig identities, you just do the same thing, but work both ends towards the middle. So it's just one more rule. All right, 1 minus tangent squared theta over secant squared theta. How about that? How do I simplify that? Well, if you're stuck, you might just rewrite this in terms of sine and cosine. I'll bet you get it. But bear in mind, it doesn't matter. If you take a long time and every step is valid, I'll count it full credit. There's no discount for doing a long proof instead of a short one. This one has a shorter one, though, if you do this. Do the algebra first. Say, when I subtract 3/5 minus 7 or something, what do? I first put them over a common denominator. 3/5 minus 35/5. And then I said, oh, that's minus 32/5. Right? So I put them over a common denominator. Same thing applies here. We write this one as secant squared over secant squared minus tangent squared over secant squared. And combine them like you did here. This is now secant squared minus tangent squared over secant squared. And now maybe you can see what to do. Maybe, maybe not. This is where you have to do a bunch of these till you start to recognize. When you see squares of trig functions, think Pythagorean identity, right? I have a Pythagorean identity involving just those two, right? It says tangent squared plus 1 equals secant squared, right? I know that. That's my identity. I can apply that at any time. So I'm done with the algebra. I go to the trig identity. That looks a lot like that. If I were just to subtract tangent squared from each side, I would have 1 equals secant squared minus tangent squared. Right? Oh, this whole expression on the top is nothing more than 1 plus 1 over secant squared theta by applying this identity. Now 1 over secant, remember, is cosine. So 1 over secant squared is just cosine squared. Using cosine equals 1 over secant to get that. So you see how having those trig identities memorized, except for the sum to product and product of sum ones aren't used so much, is real important in being able to simplify and prove identities. So this complicated expression was nothing more than cosine squared. Now, if you get stuck here, and this is a hard identity to remember, what you can do when you're stuck is try writing in terms of sine and cosine, right? This is 1 over cosine squared. This is sine squared over cosine squared, and this is 1 over cosine squared. I'll bet you can do it with a bunch more steps, because then what happens is somewhere along you'll see sine squared plus cosine squared, and that will go to 1 instead of this one. So with a longer proof, you can convert it into sines. Simplification, you can convert it into sines and cosines, and you'll probably figure it out. That's the beauty of that one. That's a very useful step a lot of times. Whenever you're stuck, try that. That one look okay? There's a bunch of others. As you have questions, come online and ask me. There's verify the identity, for instance, in number 9 is a really useful one. I guess I'm about out of time. It's 12:15, so I better quit here. Come see me as you have problems. If you can do all these kinds of problems like this, especially the longer ones, I think you'll be in good shape for the test. This is a small smattering of these is what it's going to be on the test. Thank you for coming in today. Don't come to class next time. It's by email.
Thank you.
All right, thank you.